Okay, so I should probably introduce the next speaker very briefly. We are running behind on time, so I'll just get to it. So the next talk, as you can see, is on finite sample smeariness on spheres. And the speaker is Benjamin Eltzner from the University of Göttingen. Take it away, Ben.
So, yes, can you see me switching the slides?
Yes. Yes.
Also in Zoom?
Yes, I have it.
All right. Okay, thank you. So I am going to be speaking about finite sample smeariness on spheres. And this is joint work with Shayan, Hundrieser, and Stephan Huckemann. And Shayan Hundrieser is actually the main author of the larger paper I'm going to be speaking about. So first I will introduce the notions of smeariness and finite sample smeariness. Then I will show some theorems on the abundance of finite sample smeariness and hopefully try to convince you that this is actually a phenomenon worth taking into account. And I will speak then lastly about correcting hypothesis tests and show you a data application. So let's start by introducing really the basic notions, namely for the distance on the sphere, we take the usual scalar product of two vectors and the R cosine. And then we can define the population and Fréchet, sample Fréchet functions as the expected square distance or the sum of square distances, and the population and sample Fréchet means as the minimizing points on the manifold of these functions. And we will also use the exponential and log maps a little bit. So you will probably all know that the exponential map is a map from a tangent space to the manifold where a vector is mapped to the point along the geodesic in the direction of this tangent vector with the same, where we take the length of the geodesic segment to be the length of the vector. So this red arrow here indicates the geodesic, and it's supposed to be the same length as the blue vector. Okay, and we use this log map to define the sample mean in the tangent space of the population mean. So, and we call the mean smeary if the Fréchet function has at its minimum at the population mean an order of less than x square essentially. And here we use this logarithm map. To have vectors in tangent space. And this basically just means that at the minimum, we cannot approximate the Fréchet function by this normal parabola, but it's flatter. And that, of course, means that essentially the asymptotic rate of this sample mean in the tangent space here is slower than 1/2. And this, of course, leads to several problems. First of all, most hypothesis tests rely on tabled quantiles, and those are based on the central limit theorem, and they cannot be used here. So because we don't have a Gaussian limiting distribution. And secondly, the asymptotic rate here, the tau, is not known in advance for a sample. So this is kind of a problem when we try to correct this. This isn't straightforwardly possible. And lastly, of course, and this is a problem we cannot overcome due to the slower rate of convergence, we need larger samples for asymptotics to kick in to get a higher power of the hypothesis test. All right. And now what do we mean by finite sample smeariness? And for that, I will introduce a helpful notion, namely the variance modulation, where we look at the variance of the data V, and we look at the variance of the sample means Vn. Sorry. And we rescale this by this factor n, and we call this n times the variance of the sample mean over this variance of the data, the variance modulation. And here I plotted the variance modulation depending on the sample size for several distributions. The blue one is a actual smeary distribution. You can see there it rises. A normal Euclidean case would be a flat line. The yellow and green case are distributions on the circle, where at the antipodal point of the mean, you have a finite probability density, which is a little less than 1 over 2 pi. So in the case of 1 over 2 pi, you get the smeary examples, and here with density a little less than 1 over 2 pi, you get the situation that this modulation, the variance modulation, rises up to a certain point and then levels off. And the last one is where I look at a mode near the antipodal point of the mean, but I cut out a little hole in this mode of different sizes here. And that leads to a situation where the modulation first rises, but then with very high sample sizes, it falls back to 1. So for very high sample sizes, we actually can work with table quantiles, but we need potentially really extremely large sample sizes. So for the red curve, you already still have an appreciable modulation for 10 equal to 5, as you can see here, or even more for 10 equal to 4. So, and this kind of paves the way to define what we mean by finite sample smeariness. As I said, we call this Euclidean if the modulation is constant 1. We call this asymptotically smeary, the point 3 here, if it diverges. But if it doesn't diverge, but its supremum is larger than 1, then we speak of finite sample smeariness. And as I already showed in the plot before, there are two cases we can distinguish, namely if the limit for n equal to n going to infinity is larger than 1, so we converge to a modulation that's larger than 1, we call this type 1 finite sample smeariness. And if it converges to exactly 1, so if it falls back off here, we call this type 2 finite sample smeariness. And this is basically just the order in which they were discovered. Yeah, so by looking at on the circle, for example, at a point mass at 0 combined with various probability densities near the antipode of the mean, we can get a great variety of different modulation curves. So the first 3 here would be type 1 finite sample smeariness. The second 3 would be a type 2 finite sample smeariness. But in between here, we see the modulation curve can have different, several bumps, going up and down due to here these probability densities near the antipodal point of the mean, which look a little funny, right? And are kind of finely tuned to give these funny shapes. But this is mostly for entertainment. Okay, now let's speak about abundance. So now I have just shown that this exists, but all the examples I showed you were sort of manually crafted to give these nice results that one can show. So how often does this really happen? So first of all, we look at the circle again, and every random variable whose support is not contained in an open half circle has a finite sample smeary mean. And unless the probability density at the antipodal point of the mean is non-vanishing, the mean is type 2 finite sample smeary, right? If you have a probability density at the antipodal point of the mean, we have type 1, otherwise type 2 finite sample smeariness on the circle. So on the circle, this picture is very simple and clear-cut. And especially as a corollary, as you know, the von Mises distribution has probability density everywhere on the circle. So the mean of every von Mises distribution is type 1 finite sample smeariness. However, if it's very concentrated, the modulation will be really tiny, right? But if it's fairly spread out, you will have an appreciable modulation. Now let's look at the same thing for the spheres. And here, if we have a random variable on a sphere with a unique non-smeary mean, which is invariant under rotation around the mean, right? And which is not a point mass, then it is always type 1 finite sample smeary. And this can already be seen from the classical central limit theorem of Bhattacharya and Patrangenaro if you really calculate what this covariance of the mean is. So this is maybe for some people not so surprising. However, I think the impact will become a little clearer in a few moments, and therefore I think it's still worth mentioning here. Namely the point is also we can actually reach with not necessarily esoteric probability distributions, arbitrary modulation, variance modulation, and arbitrary magnitude of finite sample smeariness, if you will. So on a circle, for example, for any value k larger than 1, there is a random variable whose mean is type 1 finite sample smeary, with the limit for n going to infinity of the variance modulation being equal to k. And especially this is also possible for a von Mises distribution. You can always pick the concentration of a von Mises distribution such that you reach a certain value of the variance modulation. And for spheres of higher dimension, there is always a rotation symmetric random variable whose mean is type 1 finite sample smeariness and whose modulation exceeds any given number. And for dimension larger than 4, this is even possible with the support of the random variable, excluding a neighborhood of the antipodal point of the mean. And the larger the dimension is, the larger this circle around the antipodal point that we exclude from the support can actually become, and it approaches really the half sphere. We always need a support which slightly exceeds the half sphere, but for m going to infinity, we get arbitrarily close to the equator, essentially, with our support restriction, and still get can get any magnitude of finite sample smeariness we like. And I think this one can also calculate this already from the formula for the covariance in the Bhattacharya and Patrangenaro CLT, but apparently nobody has done that, or nobody pointed that out or found that. So therefore, I think it's still worth mentioning this. Okay, so what can we still do in the case of smeariness? And what we are first looking at will be a simple simulation for von Mises data, where we are looking at two von Mises distributions with a concentration of 1/2, right? And different means. So mean one has mean 0, one has mean p, and we see if we take the quantile-based test, we don't get the correct level, right? The correct level is supposed to be 5%, which is indicated by the dashed line. And if we use the bootstrap, we actually get the right level. But one already sees here, due to smeariness, the power of the test is lower. And this is not because we use a suboptimal procedure. This is just because of the slower convergence rate, right? So we have less power. Right, but using the bootstrap, this is just the upshot. We can actually make meaningful hypothesis tests, although we can never solve the problem that we just have a slower asymptotic rate. And in application, we have looked at a number of wind data sets for different years and different towns, namely Basel in Switzerland and Göttingen in Germany. So those are daily mean wind directions over a whole year. So just taken as a kind of a histogram of wind directions, if you will, or a data set of wind directions on the circle. And as you can see here, they are typically bimodal, because in winter you often have northeastern wind no, in the summer, I think. So what the upshot here is simply that the quantile-based tests gives wrong p-values, and if you use the bootstrap corrected test, only one of these tests comparing the mean wind direction will actually reject. And we did a little more using at a larger data set of years, where it turns out that the years 2003, 2005, 2017, and 2018 appear exceptional because they are really different from many other years. And it turns out 2003, 2005, and 2018 were some of the hottest summers. And this actually meant that you had a lot of unusual wind patterns in the summer. And 2017 was, I think, in Southern Europe, a great flood year. So those are meteorologically exceptional years also. Yes, and for the full paper, please look on the archive. Thank you.
Okay, so we have one question here from the chat. Can you give some more insight into the rotational symmetry assumptions? Is it only for rotations around the vertical axis, and why is it important?
I always mean rotation around the mean. And this is a simplification because you can easily calculate that. We are pretty sure that this holds for any probability distribution which is not restricted to a geodesic, so a great circle, to a half great circle. So if you take an open half great circle on the sphere and you have a probability distribution on that, you're in the same situation as the circle, and you have a unique, you have somehow, you shouldn't have smeariness. But as soon as you have kind of a two-dimensional support, we expect smeariness, but it's much harder to show. Rotationally symmetric distributions are somewhat easier to calculate. That's all.
No more from the chat. Any in the room, perhaps?
Yeah, maybe I have one. Oh, please go on.
So I want to say thank you. I think your work is extremely interesting. My question is the smeariness of you consider the smeariness of sample means with respect to population. It would be also quite interesting to look at the smeariness of online recursively computed means. And so do you have any maybe
of what the online means?
Online means.
Recursive.
Recursive.
You mean something like the nested mean of a recursive dimension reduction, or I'm not really aware of what you mean.
It's just,
sorry.
Just different algorithm to compute the mean by approximating.
I see.
With 1 point at a time.
You could do it with one sample at each time. It's recursive.
Same effect. You get the same effect.
Yeah. At one point.
So you would get the same effect. I think the answer is you would get the same effect.
But this is simply a different algorithm to calculate the same quantities, the same minimum of this function, or?
It's another algorithm.
Okay. This shouldn't depend on the algorithm. I mean, to be sure, on the circle, we have actually an algorithm that's guaranteed to give the mean for a finite sample. On the circle, this exists. On the sphere, we actually did a Gauss-Newton type minimization. However, we used 10 starting points so this typical damage mitigation approach, and we're pretty sure that it works really well, effectively, right? So it shouldn't really depend on the algorithm. We have tried the Gauss-Newton type minimization. I have also once tried this this one where you start this repeated mean on the tangent space and then moving to the new mean on the manifold with the exponential map, right? And then taking there again the mean on the tangent space and so on. So this is a quite fast converging iteration that's I think been proposed in the context of shape spaces, and that usually leads, if you also start that 10 times with different initial points, that usually leads to the same result.
Okay, maybe we can thank the speaker.
So yeah, those talk is on the same scope.
Okay, so this one.